Against what most people think, the gravitational force or the gravitational strength varies from one location to another on Earth. Not every location on Earth have the same gravitational field, and not every location on Earth have the same gravitational strength. So here we see a scientific curve that represents the latitude or the height or how far you are from the surface of Earth versus the magnitude of gravitational field strength G. The unit for the gravitational strength is Newton per kilogram, and the latitude could be in meters or in English units. So at 0, that's where the equator of Earth is, and here where the poles are. As you know, the Earth is not a full sphere, not a full circle, if you will. On the poles, the Earth is more flat. On the equator or at the equator, the Earth is kind of plunged to the outside, shaping an oval cross-sectional shape. So you can see here, as you're moving from the equator to the pole, the gravity is becoming higher. That is because you are getting closer to the center of the Earth, while on the equator you are the farthest from the center of the Earth, where the magnitude of gravitational strength is being decreased. So we can summarize that the value of G increases as you move toward either the north or the south pole, because Earth is not a perfect sphere as we mentioned, but on the poles it is flat and it is slightly bulged at the equator. The Earth radius is known to be 21 kilometers greater at the equator than at the poles. So the object at the equator is more far away from the center of the Earth than the object in the north or in the south pole. So with that being said, we can give a relation between the gravity, acceleration, and the radius of Earth. And this relation, the smaller the r means the closer you are from the center of the Earth, means the higher the gravitational acceleration. The bigger the r, the smaller this number 1 over r squared, it means the smaller the gravitational acceleration. In more comprehensible terms, the farther an object from Earth's center, the smaller the value of G will be. Scientists did all the research and all the experimentation needed to be able to draw a map that we call it the Gravitational Strength Map for the Earth's surface. And this map looks like this. Red areas means the gravity is in its highest values, and the yellow and green and blue means the value of gravity is less in those areas. So this kind of analysis helped the scientists finding the rare earth metals and finding all kinds of materials on the surface or under the surface of the Earth, because there is a relation between the value of gravitation and what kind of material is that part of the Earth is made out of. So that variation in the value of G on Earth can help detecting the minerals and oil, so that the geophysicists and geologists use sensitive instruments, what we call is gravimeter, which is a sensor that detects the value of gravitation, so that the small variation in G can be detected when they are searching for a new deposit of ore or oil. Gold and silver deposits increase the value of G, while the deposits of oil and natural gas decreases G. And that help you finding all the minerals under the Earth, either liquid or solid minerals, by defining the value of the gravitational acceleration. As we are learning about gravity, gravitation, gravitational forces, and gravitational field strength, it is important to know what is the difference between the true weight and the apparent weight of an object. Up until this point, we use the equation, the gravitational force Fg equals the mass by the gravitational acceleration G. so that we can calculate the weight of the object. Weight of the object equals mg, and weight of the object at any location in the universe can be calculated using that equation. The gravitational force that you find through that equation is called the true weight. So to find the true weight of the object, you use Fg equals mg or W equals mg. That is the weight of that object in the universe. To understand the apparent weight, let's assume there's a student standing on a scale that is being calibrated in newtons in an elevator. So that's the scale. The student is standing on the scale, and this is the elevator. He can choose to go up and down on that elevator. While the elevator at rest or moving at a constant velocity, the scale reads 600 newtons. So the weight of the student naturally is 600 newtons. But when the elevator starts to move up and down, those numbers vary, and we need to understand why those numbers vary and how does that help us in understanding physics. We can start with drawing a free body diagram of the object standing in the elevator. While the elevator at rest, we know that there is an Fg. That's the weight of the student pulling downwards. You have the normal force starting from the surface of the elevator pushing upwards. Acceleration is 0, assuming the velocity is constant. So we found the true weight for the student by applying F equal mg. Now if we do an analysis for the forces, the F net on the vertical axis for the student equals the Fg plus the Fn. We know here F net is 0 because the elevator is moving in a constant speed or at rest, either way. So this case tells you Fg equals minus Fn or Fn equals minus Fg. But since the Fg is pointing downwards, and assuming the convention upwards is positive, downwards is negative, that's what we set as a convention here. Fg is equaling minus mg, and the F normal is positive. So F normal would equals mg. So a student standing in an elevator, F normal would equals mg. So if the F net is 0, the magnitude of normal force equal the magnitude of the student weight. That's one thing. Now, what if the elevator is accelerating up uniformly? In this situation, the scale will read 750 newtons. Why is that? Based on the free body diagram, we say F net equals Fg plus Fn. And we know, in this case, F net equals m by a equals Fg plus F normal. F normal equals mass by acceleration minus the Fg by re-preparing the equation. And Fn would equal m by a minus the m by g. You can take m as a common factor. F normal would equals mass multiplied by the acceleration minus the gravitational acceleration. Now we know the mass and we know the g. In this case, you can tell that the weight of the students is changing if we have all the variables needed to solve this kind of problem. So the equation for the F normal valid, whether this is accelerating up or down. Now in the graph you see down here, the student is feeling heavier than usual because the scale is pushing up on him with a force greater than mg. So as you saw in the previous figure, the student feels heavier than usual because the scale is pushing up on him with a force greater than mg. Now, if the elevator is accelerating downward uniformly, the scale would read less than normal weight. That would be 525 newtons, and that can be explained by having F normal equals the mass by acceleration minus g, but the acceleration is pulling downwards and the gravitational acceleration is pulling downward. Those are working against the normal force and the mass is constant. So A and G are in the same direction. So the F normal would be less than the mg and the student will feel lighter than usual. And the scale would read as 525 instead of reading 600 newtons. So the quantity minus F normal is called the apparent weight in this case. His real weight is 600 newtons, but he was reading 525, or sometimes when he's accelerating up, it is reading more than the normal weight, while the elevator accelerating down, it is reading less than the normal weight. That is the apparent weight or the virtual weight for that object. So for the situations we discussed, the equation for the apparent weight of the student can be represented as weight equals minus normal force, which would equal minus m by a minus g, which would equals m by g minus a because of the minus signs over here. we can flip those two variables and the equation is still right. So the weight, the apparent weight for the object equals minus normal force, or equals the mass by g minus a. Now let's take an example on the topic. There is a 100-kilogram astronaut in a spacesuit standing on a scale in a rocket. The acceleration of the rocket is 19.6 meters per second squared up. Find the true weight and apparent weight during liftoff on Earth. The acceleration due to gravity on Earth's surface is 9.81 meters per second squared down. So up is positive in convention, down is negative. You have an astronaut in the rocket around him, and you have a scale below him inside the rocket. The rocket won a launch from the surface of Earth before he escaped the Earth atmosphere, still in the Earth lows. In this case, we're given mass equals 100 kilograms, acceleration 19.6 up, gravitational acceleration equals 9.81 down. Find the Fg and the weight. So the true weight, which is the gravitational force weight, and the apparent weight, which is W that we found previously. Firstly, we draw a free body diagram for the astronaut. We have gravitational force pulling downwards, we have normal force pushing upwards, and drawing the vector schematic for those forces, you have F net pushing upwards. Now, using the equation Fg equals mg, we find the true weight easily. We have the mass and the gravitational acceleration. That would give you the weight, or the true weight, of the astronaut, minus 9.81 by 10 to the power 2 newtons. So the astronaut is not accelerating left or right. That tells us in horizontal direction, the net force equals 0, of course. So for the vertical, we have the F net equals the F normal plus the F gravitation. We found the F gravitation. The F net can be represented as mass by acceleration equals F normal plus the gravitational force. F normal, if you rearrange, would equal the mass by acceleration minus the F gravitation. The mass is 100 by 19.6 minus the 9.81 by 10 to the power of 2 newtons. And normal force for the astronaut, applying on the astronaut, equals 2.94 multiplied by 10 to the power of 3 newtons upwards. Now back to the equation. The apparent weight equals minus the normal force. We know that normal force equals this much. The apparent weight would equal minus 2.94 by 10 to the power 3 newtons.